Hi everybody, my name is Erwin Mazwardi. In this video, I'm going to walk you through the R code used to build the decision tree and neural network models. These models were part of the articles on Medium titled Which Learns Better? A comparison of neural networks and description trees for predicting unemployment rate. If you like to get a deeper understanding of what each part of the code is doing, I have included in the link to the article in the description below. Feel free to check it out for more details. Let's get started. Let's walk through the R packages we are using in our unemployment rate prediction project. These libraries help us load, clean, visualize, and model our data, all in a reproducible way. The first one is data import and manipulation. We start by loading data from Excel, cleaning it with dplyr. Lubridate helps us manage any date fields like converting strings to proper data formats. Next is for visualization tools. So ggplot2 is our go-to tool for data visualization. Coplot creates correlation heat maps. psych include pairs panels for checking feature relationship. Next is modeling libraries. This is the modeling powerhouse. So we are using rpart for decision trees and for neural networks. Caret simplifies training and cross-validation. PIP shows us what variables matter most. Don't forget this rpart plot actually is to visualize decision trees. The last one is the model evaluation metrics. So we use metrics to evaluate our models. For example, calculating how far our prediction are from the real values using RMSE, MAE, and so on. Alright, in this line we are reading Excel file called ausdata into R. We are using the read Excel function and we set call types to text. That means all the columns will be imported as text, which can help prevent automatic type conversions that might cause problems later on. The data gets stored in a variable named raw data, so we can process or clean afterward. Okay, step 3, create a copy of our raw data. Here we create a copy of our raw data and call it clean data. We forgot to run this. Let's run this one first. And then this. Here we create a copy of our raw data and call it clean data. This way the original raw data stays unchanged and we have a separate version to clean and process. So keeping both copies make it easy to compare or start over if we need to. Okay, step 4. Here, in this line of code, we are giving our data columns new names so they are easier to work with. We use call names to set the names of all columns in the raw data. This helps us know exactly what each column represents when we look at the data or write more code later. Okay, in step 5, what it does, this removes the first row from clean data. It helps clean up any unwanted extra rows before we start analyzing. Okay, we run this one first and then step 4. As you can see from here, it removes the first row, which is this long names, period, unemployment rate, gross domestic product, general government, and so on. Alright, so now we continue step 6. So what it does, this part changes columns 2 to 9 into numbers. It makes sure all the data in those columns are numeric, so we can do calculation without errors. This is the function that we use to convert to numerical data. Okay, we run this one. Right, so you can see the difference. For example, this is still string GDP 1.6, but this one is already numerical value. Then 7, what it does, basically this converts the PER column into proper dates. So this is the original PER columns, right? But we need a proper date. And then this is the format that we use to convert. So it uses the origin date, so the numbers turn into real calendar dates we can work with. Let's try it. See, now this is the proper date. Number 8, Okay, the first line here actually we'll find that NA exists in this column JV and RP, and then we clean them, right? This is not clean actually, so we replace them with the average of the known NA values. Let's run this one. So as you can see, the first line, JV and RP has NA's values, but after we clean the NA's, we replace it with the average, and then we run this function again, and then it falls. Alright, now it cleans now. No NA values anymore. Alright, step 9. So here we're checking how the numeric columns relate to each other by calculating their correlation. First, what we do is we remove the first two columns with clean data. Since those might be date or target variables, we don't want in the correlation. We remove this one. Okay, let's run this. Then we use the co-functions to create a correlation metric showing how strongly each pair of variables is related. Okay, number 10, to visualize it, we call coplot. Okay, let's run it. Let's look at the parameters. Okay, type is upper means we only show the upper triangle of the matrix, so it's less cluttered. This is the upper triangle of the matrix, as you can see from here. And then order Hetzilas reorders the variables based on clustering, grouping similar variables together visually. TL.call set to black means the text labels to black. So this is text labels to black, so they are easier to read. TL.cex 0.5 makes the label text smaller, so it all fits nicely. TL.srt 90 rotates the text labels to 90 degrees, putting them straight up and down. So this combination gives a clear picture of which variables are strongly or weakly correlated. Number 11, step number 11. First, we make a copy of our clean data and call it class data. And then we round the UR column so it's easier to use. Step number 2. Then we create scatter plots for all the variables with histogram and correlation ellipses. Okay, this is actually, we use these pairs panels. So in pair panels, we set up how the plots look. So let's run it. Let's try to understand the parameters here. So the first one, actually, we remove the first column, in this case dates. So we only plot numeric data. Gap equal to 0 means there is no space between the panels. PCH21 picks the point style for the scatter plot. Histogram columns colors the histogram on the diagonal, so this is the color. Density true means add smooth density curves on top of the histogram. See this one? Ellipsis true shows ellipses around the points to visualize correlation. BG sets the background color of each point based on the UR groups. Alright, so this is the background colors. So together this makes it easy to see how variables relate and spot any trends and all clusters. Step 12. So box plots are made for all columns except for the first two. They show how the data is distributed and highlight any outliers in each variable. Okay, we run this. Now we are going to scale the data. First, a copy of the clean data. Alright, a copy of the clean data is made and called scaled data to keep the original safe. Next, all columns except for the first and two are scaled. Okay, this is the function. Are scaled so their values are standardized. Finally, the 108th value of UR is set to very small number to prevent any problems with zeros or missing data. And then we run the box plot again. See? Can see different now, right? The scale data has been normalized here. The next step is to create a decision tree model here. First, what we need to do is the data is split into training and test sets based on the PER date. All rows before the 1st of March 2018 go into train data and the rest go into the train data. Okay, so this is actually will split into training and test sets. And then next, Okay, a formula is set up to predict UR using several input variables like GDP, GFCE, and the others. And then the random seed is set for reproducibility, so results stay at the same each time you run the code. Then a decision tree model is trained using the rpart function with an ANOVA method because the target variable is continuous numerical. And finally, rpart.plot displays the tree so you can see how the model makes its splits. Okay, let's try it. Alright, next is we check the variable importance of the D3 model using this VIP function. So as you can see that RP, CPI, and GV play very important roles in predicting the UR. We go to number 16 now. So what we do, we are going to evaluate the decision tree model performance on the training and test data. So predictions are made on training data using the decision tree model. So this is the model, right? And then we predict it. The RMSE is calculated to measure how well the model fits the training set, and the result is printed out. Next, predictions are made on the test data to see how the model performs on unseen data. The RMSE for the test set is also calculated and printed, so you can compare training and test performance side by side. Okay, let's run this. So this is the result. Estimated training performance 0.5 and then estimated test performance is around 0.75. If you want to understand what does it mean, please read the article that I wrote in Medium. Alright, step 17. We specify parameters for cross-validations. Why do we need cross-validation? I already explained in the article I mentioned before. Alright. So random set again is set so our results are reproducible. Okay, we set it to 1, 2, 3, 4. So you can give any number here. Then next, the training control function sets up repeated cross validation for 10 faults. Okay, this is method repeated. Number of faults is 10 and 5 repeats. Repeat 5 times using a grid search to tune the model. Now we perform cross-validation. Again, the seed is set again to make sure the model training uses the same random splits. Then a decision tree model is trained with cross-validation on the training data. This is the training data. Then we use the control that we have specified before. Alright, okay, let's look at what each part of the train function does. Run this. This is the formula telling the model which variable to predict and which variables to use as inputs. Data equals train data means this says to use the train underscore data dataset to build the model. Method rpart. This tells Caret to use the decision tree algorithm from the rpart package. TR control. This applies the cross-validation settings you defined earlier in the train control, including repeated cross-validation, number of faults, 10 faults, and then 5 repeats, grid search for tuning. Okay, number 3, and then actually we plot this line, draws a plot of the final decision tree model so you can see how it splits the data and which variables are used for each split. Okay, number 19. Why does actually we are going to run the model performance here. So in step 1, the training performance is shown by extracting the RMSE and formatting it nicely. Predictions are made on the test set and the RMSE is calculated to see how well the model performs on unseen data. Okay, we've done with creating the DT model. Okay, next, we are going to proceed with neural network. So here, first what we need to do is we need to do the min-max normalization of the scale data set. Okay, so this is the function for the min-max. And then we normalize the data set, the scale data, apply to all columns except for date column. So each variable ends up on the same scale using this normalize underscore max underscore min. So we added back the PR column to keep the date information. Next, the data is split into training and test sets based on the date again. A formula is set up to predict UR using several input variables. a hidden layer configuration is defined for the neural network with 5 neurons in the first layer and 2 in the second. You can configure with any neuron actually. And now we run this. Alright, we continue step number 21. What we do, a random seed is set to make the neural network result reproducible. Then the neural network model is created using the training data. Even though the data includes the PER column, is not used in the training because it's not part of the formula. The network uses 2 hidden layers with 5 and 2 neurons, and linear output is set to false, means the model will apply an activation function to the output, which is common for classification or scale targets. The training stops when the error drops below 0.01. Finally, the network structure is plotted so you can see the layers and the connection. Run this one. Now we go to step 22. First, the code gets the minimum and maximum UR values from the original non-normalized training data here. So we have this is the scale data, okay? It's not the normalized one. We assign that to train data original, alright? And then we get the minimum and the maximum values of the UR. Alright, for the training set, it prepares the input variables. Okay, we prepare the input variables here. And then next is we compute or we make predictions with the neural network, and this is the model that we have created. And then we combine this one, the prediction with the actual normalized values. Number 4, the predictions and the actual are then converted back to their original scale using the min and max. Okay, this is the min and max. And then we use RMSE to measure how well the model fits the training data. So for step 3.1 until step 3.5, the same steps are repeated for the test set: selecting input, predicting, denormalizing, and computing the RMSE to see how the model performs on new unseen data. Finally, the training and test RMS values are printed out so you can compare them. What is telling you that the training RMSE 0.83 and then test RMSE 1.02. Is it good? Okay, read the article that I wrote. Alright, and then we continue with the cross-validation of the neural network. First, 5 faults are created for cross-validation by splitting the dataset into equal parts. Okay, this one, cross-validation. A list of different neural network architectures is defined. This one, right? Is defined, each with a different number of hidden neurons and layers to test. Create an empty data frame to store the results for each architecture's performance. Right, in step 24, we loop through each configuration. So what it does is, for every architecture, it runs 5 iterations, right? This one, 5 iterations. One for each fold of the data. In each iteration, the data is split into training and test sets based on the current fold. A neural network model is trained using the training set and the specified hidden layer configuration. The minimum and maximum UR values from the original training data are saved to help convert predictions back to the original scale later. Next is prediction are made on both the training and test sets. These predictions, which are still normalized and then converted back to the original units. RMSE is calculated separately for the training set and the test set, so you can see how well the model fits the data it learned from and how well it generalizes to new data. After all faults are processed for a configuration, the average training RMSE and average test RMSE are calculated and saved to the results table. Actually, this is the one, the second line. Finally, once all architectures have been evaluated, the results are printed out so you can compare which configuration perform best. So we repeat the above process with the test set. Exactly the same procedure. Let's run this. Okay, and then we run this. What we can see from here, actually the 3-2 configuration, this one actually has the lowest RMSE, the lowest average trained RMSE compared to the rest of configurations, meaning it predicts best overall. The trained RMSE is reasonable, not super low, so it's not overfitting badly.
Alright, that's it for today. I hope you found this presentation helpful and learned something new. Thanks for watching, and I'll see you in the next video. Take care.